Welcome once again to another investment analysis video. I would now like to continue with our examination of the concept of utility of wealth functions, and we'll do so by looking at another example on a spreadsheet. And in this example, we assume that we start with $50,000 of wealth, and that a risk appears, probably best understood by assuming the risk appears after markets close. And we pretend that we know that the risky distribution of possible outcomes, given that the risk occurs, is a 40% probability of ending up with 30,000, a 30% probability of ending up with 40,000, a 20% probability of ending up with 50,000, and a 10% probability of ending up with 70,000. So this is our risky distribution of possible outcomes. It differs from the prior example in the earlier video in that we have multiple outcomes. We have multiple outcomes in excess of 2. We have 4 possible outcomes here, and these are the values. Now, in this example, we're going to specify a utility of wealth function, and it just shows here U equals 15 times the natural log of wealth, and because it's a logarithmic function, we know that we're assuming our investor is risk averse. Okay? Now, the first thing we do here is, given that we have $50,000 of wealth, is we calculate our original utility of wealth before this risk appears. And all we do is plug 50,000 into this equation, and when we do that, we take the natural log of 50,000, multiply it by 15, and we get 162.2966743. So that's our original utility of wealth. Okay? Now, at issue here is, what is our expected utility of wealth given the arrival of this risky distribution of possible outcomes? Okay? And we can see that it's calculated on this table. But before we do that, let's quick calculate the expected value of wealth given this RDOPO. And so we're just going to take 0.4 times 30,000 and add to that 0.3 times 40,000 and add to that 0.2 times 50,000 and so on. And that's what we have in these columns here. And lo and behold, when we sum these, we get 41,000. So the expected value of wealth given the RDOPO is 41,000. Now, it's impossible for us to end up with 41,000 given our assumptions, but that's okay. That's what the expected value of wealth is. Next thing, we want to calculate something that's important, the expected value of utility given the risky distribution of possible outcomes. And to get that, what we're doing is, instead of multiplying 0.4 times the 30,000, as we did to get expected wealth, we're going to multiply 0.4 times the utility associated with having 30,000. So we calculate this in this cell right here, and what that is 0.4 times 15 times the natural log of 30,000. In this cell here, we have 47.6848563, and what that is 0.3 multiplied by 15 times the natural log of 40. This 32.459 is 0.2 times 15 times the natural log of 50,000, and this 16.734, etc., is 0.1 times 15 times the natural log of 70,000. And so the expected value of utility of wealth, the expected value of utility of wealth, expected value of utility, is 158.73222829, and we of course notice that that expected value of utility is less than what we started with, 162.2966, etc. Okay? So we see that immediately upon the arrival of this risk, that the utility of the investor falls. Okay, that's a very important observation. Immediately, his utility falls. Well, we then consider, what amount of wealth, if we had that amount of wealth for certain, would provide us with 158.7322829 utils. And to get that, what we do is we plug this expected utility of 158.7322 in for this utility value here, and we solve this equation. So we have 158.7322 equals 15 times the natural log of W, okay? Well, the first thing we do is we divide 158.7322 by 15, and we realize that that's equal to the natural log of W, okay? And then what does that mean? Well, that means that 158.73 divided by 15 is the exponent that we have to raise E, the base of natural logs, to get the value of wealth. Since 158.7322 divided by 15 is the natural log of wealth, again, we then have to raise E to that power. What power? 158.7322 divided by 15 to get the value of wealth. And since we use the expected utility for utility, this wealth is a special wealth. It's the certainty equivalent wealth we talked about in the prior video. Okay? And that's calculated right here. And the certainty equivalent wealth is 39,424.87. So the certainty equivalent wealth is $39,424. The next question we ask is, well, what is the maximum amount that this investor would be willing to pay to avoid this risk? Both the upside right here and the downside here and the no result there. What is the maximum amount the investor would be willing to pay? Well, the investor would be willing to pay the original wealth of $50,000 minus the certainty equivalent wealth of $39,424, or $10,575. So the maximum insurance premium that this investor would be willing to pay to avoid this risky distribution of possible outcomes, assuming that an insurance policy of some type were to be available, would be $10,575. So this example on this spreadsheet is showing a slightly more realistic version of a potential circumstance where we have a risk appearing after the close of the markets, where we can't trade out of our positions immediately. Rather, we have to wait until the information, is fully disseminated, and hence the assumption is that the next day the result, whatever it is, will be fully incorporated in the prices of the assets in the market. That's all I have for this video. Thanks for watching.